So yes, it's the last session. I know everybody's frazzled. I know my brain's frazzled, so I'll try to keep it somewhat interesting, and we'll skip through a few things depending on time. So human mobility, but first, maybe just a little about me. So by now, most of you have probably heard I work for BAE Systems, and most people, think about the large, the submarines and the jets and things, or the cybersecurity part of it that the company does. Well, most people don't know is, for example, some of the stuff that's on the Mars Curiosity rover comes from us. Apparently, we build hybrid propulsion systems for buses. We do a lot of work with UK sport, especially leading up to Olympics. Behind the scenes, there was a lot of work done supporting the teams in quite a few disciplines, and that work's still ongoing. Really, really interesting stuff. I also organize the London Algorithms and Deep Learning Meetup. I'm currently, in the steering committee of a new community we're founding, which is the UK Community of Research Software Engineers. So I also, for the last couple of years, been working as a STEM ambassador, so doing lots of outreach, working with children and kids in secondary schools, and try to get them enthused about science, technology, engineering. Currently, I'm working with a local school with 2 teams and getting them to build little underwater robots. So really fun stuff, really enjoy it. I also do a lot of work on the hacking for humanity or technology for social good kind of scene. So, besides the talk, if there's anything, people do in any of these areas or interested in, please, come talk to me. Anyway, so human mobility. So I'm going to report here on a project that we did in collaboration with the University of Southampton. I'm just one portion of this. A lot of the heavy lifting here was done by James McInnery as part of his PhD. This was his PhD topic. He really went into the nitty-gritty, build up the models and everything. So when if you have detailed questions about the modeling, about the inference, or etc., I'm really not the right person to ask for. This is a relatively new domain for me, but it looks like I'll be inheriting this project and take it forward, so it's a good exercise. So with a number of people at the University of Southampton, James especially, somebody at BAE. And the main part of this work was published last year in Pervasive Mobile Computing. And also for this particular bit of work we built on top of that, we've just submitted a paper to KDD, so hopefully that'll get accepted. So I'm just going to talk about the work that was done here. So human mobility. All of us, we all walk around with smartphones, or we take the tube, or there's various ways our movements are tracked. And there's lots of data out there, and you can make some pretty pictures. So this is taxi rides in Beijing by somebody at Microsoft Research. So mapping all the pickup and drop-off points, and you can see some patterns and you can create pretty pictures. But there's some information there. Closer to home. So I think many of you will probably already seen this. It did the rounds a while ago. So this is mapping Oyster cards here in London. And you see, going through the day in the morning, everybody kind of, there's this massive influx of commuters all going towards London. And so as people go to work, it settles down a bit. As you go towards lunch, there's a bit more movement. And then as you go towards 4 o'clock, people start to go home, and the city empties again. So this is just tracking Oyster data. So you can there's lots of data being collected. You can generate all kinds of very interesting and pretty pictures and movies and things. But of course, what you're interested in is what can you infer from the data. So if we look at the taxi data, for example, again, you could look at that kind of data, but as other sources, we look at what are the functional zones in my city. Can I discover them from the data, and do they match up with what I'm trying to turn the city into? So does it match with the official planning records? So you can look at taxi rides, or you look at public transport uses and various things. So you can say, okay, from that, can I deduce, where do all the people go to party? Where are all the restaurants? Where's the financial district? Where are the functional zones of my city? How does that break up? For tourism is another obvious application. So where are the touristic hotspots? How do people move between those hotspots? And can we use that information to improve public services, etc.? So this is just a different example, I think, again from London. But so this is looking at a particular, I think, a bus line which first ran. So this is the first stop, and it used to run up to here. That's where the bus line would terminate. But then they extended the bus line to where's the mouse here? Yeah, they extended the bus line to here. And so you can, it's easier this way. So you can see here, this is just a curve of how many passengers use the line. And you can say, okay, we've extended the bus line from there to there. What's the impact on passenger volume? Well, you can see, yes, it's generally gone up. But it hasn't just gone up here where we've extended the line. Of course, there's an impact which you can trace back. Interestingly, it only starts from here. So the people right at the beginning, they don't really seem to care about going to right at the end, but the people here do. And you can look at the various bus stops and where do people get off and where do people get on, and has that changed now we've extended the line? And you see generally that this is where people got on before the extension. This is where people got on after. You see generally more people got onto the bus, which you can see by the volume here. But you can look at various patterns, and so interestingly, a lot of people get off at this stop, which is just one stop further than where the previous line ended. You could look at these kind of pictures. You start to reason and try to think, why is this happening, and how can I use this kind of information to improve my service? So generally, human mobility is actually it's a really interesting domain, and there's cross-cuts with many different fields, going from sociology to epidemiology, computer science, even physics. And there's lots of interesting work done here. I mean, the figure on the left, so this is, I think, work done by MIT. So if a person visits, let's say, 5 locations, there's 5 factorial ways he could visit those locations, many different ways he could visit those locations. But turns out it's what people actually do. They don't visit all the permutations of these possible locations uniformly, but there's always a particular sequence people follow when visiting a certain set of locations. So there's a particular pattern, what they call a motif. And you see this motif appear on different levels, so not just the very low level, I go to work type thing, but also on a higher level, how do communities move and things, and how across large distance. But there's structure there. That's what really I'm saying. And taking a very high level view, if you look on the right, how do population groups move? And in this case, how did humans colonize the Polynesian islands in the Pacific? And so you could look, how people moved and why they moved, and there's lots of interesting things you could infer there. And yeah, just to say this is all very relevant. Just 2 weeks ago, Yahoo and Carnegie Mellon announced a £10 million project to look at how can we predict human needs and human intentions, especially focusing on the spatial side. So that's just some intro. So human mobility. So I don't know who was here yesterday, so Eric Drass, the guy with data and art, he mentioned that human mobility is very, very predictable. People are very predictable. The average predictability for the next hour is 93%. So if you know where you are, if somebody knows where you are now, you can guarantee quite to a large degree where you'll be in the next hour. And the distance doesn't really have an impact. So it doesn't matter if you're traveling 10 kilometers or 10,000 kilometers, but the pattern is actually very, very regular. So there's a high degree of regularity, so both spatially, as into what kind of locations you visit, as both temporally. So what you do in the week, there's a pattern there. In the weekend, it's different, but so there's a lot of predictability there. And this is just saying the same thing, but just graphs, and people have published papers about this, and you find various plots. But you look here, there's the number of travel activities you make. So for every day in the week, you have a line, and so these are all the weekdays, and you see they all pretty much coincide. So the pattern for a whole week is very regular. In the weekend, the pattern is different, but still, it's extremely regular. And you look, those two plots essentially show the same thing. So for every day in the week, you have a certain pattern. But in the weekend, this is when, of course, things get a bit less regular because, you don't go to work, you go visit family, you go take a weekend off or whatever. So there's a lot of temporal regularity in people's movements. Same thing for spatial. So if you look at all the locations people visit, there's actually only a couple which are really important and those people visit a lot, i.e. where you live, where you work, maybe where your parents live, or depending, or maybe if you go to football club or something. But there's only really a couple locations where people visit really, really often, and there's also quite a well-defined pattern between those locations. And you can plot those as graphs, and the bigger the node, the more important the location is, and you can do some interesting things. However, so okay, people are generally very regular, and this has been known for quite a while. So that's good, and you can try to learn those patterns, and that's what people like Google and Facebook, et cetera, do. But the particular work Southampton was looking at, and we collaborated with, was what happens when people deviate from that routine. So, because that's actually, that's actually interesting. That's maybe particularly more interesting than the pattern in itself, is when do people break from these patterns? So, instead of going to work, you're ill and you stay at home, or you decide to take a weekend break or something. And these are potentially interesting events. And so tying it back to the technology, so being in an unfamiliar place, an unfamiliar time, you would think that intuitively that you would help you if you had extra context-aware assistance. So if you're thinking about phones and apps, if you're somewhere unfamiliar at an unfamiliar time, you'd be likely a higher demand for needing maps or hotels or mobile advertising could be made more relevant. And it's actually quite ironic I say that now, because yesterday after the party, I was getting my train back to Southampton, got on the train, got onto Clapham Junction, but then turned out that somebody, poor soul, had been hit by a train further down the line, so essentially the line was closed and the train wasn't going anywhere. So I was essentially stuck. So at that point, I was in a place I'd never been before, and I need to decide what to do. So you pull up your phone and you in that time, I really needed some kind of more information about, okay, where's a hotel, where can I stay, et cetera. So it's these kind of things, these kind of breaks in the routine which are interesting to look at. So can we characterize it? Is there a pattern there? Can we model these? Can we predict these? That's the goal. So there's lots of different applications, both for in the learning a person's mobility pattern, but also learning about when does the person break from this pattern. Going from optimizing public transport to insight into social behavior, how people interact. Spread of disease is a very obvious one. Recommender system, so everybody knows about Google now, so it tries to predict where you're going to be in the next half hour or so, and it will give you traffic information or weather information or whatever. So that's exactly what they're doing. Sherpa is another one. Context-aware advertising, obviously law enforcement, there's a use there. Urban planning, and there's lots of applications. But of course, obviously, as Eric rightfully mentioned yesterday, this is data about how you move and your patterns, and there's obvious privacy and de-anonymization concerns there as well. So just I think he made the point well, but just be aware of that. So just a concrete example. So the London riots. So all the red dots are where particular crimes occurred. So the riots, and there were particular crimes being recorded. Those are red dots. And the blue dots are the people who actually did the crime. And the blue dots start out from where these persons live. So you know who did the crime, you know where they live, you know where the crime occurred. And then you can figure out, okay, what's the most likely route they took from their home place to the scene of the crime? And is there something you can learn for that? So what can we learn about how how they congregated, or what's happening there? So this was done, I think, done by some company, but the video comes from The Guardian.
How did you get the information?
Oh, so this is something that I wasn't involved in. So this is just if you look for examples, this is something that The Guardian published an article about.
No, but you found the people who committed the crime. You traced back.
Oh, yeah. So that you have to ask the police that. So somebody commits some crime, maybe they catch him on CCTV or something. No. So this. Sorry.
It's true, not fiction.
Yeah. This is not fiction. I mean, this is real data from riots happen. If you own a store and somebody takes TVs or something, you go to the police, you report it. They try to find who did it, and that kind of data you can use for these kind of things.
Police actually published photographs on Flickr with their
Oh.
not addresses but the streets that they lived on.
Oh, really? Okay. So well, there you go. That's interesting, though. That you'd think that'd be an issue. Okay, interesting. Right. So I mean, that's just an example of, in this case, inference. So you're trying to infer from a person lives to some else, and what's the most likely path there? And if you can, and that becomes easier if you know more about that person and his regular pattern, etc. So we want to model mobility. So the problem, the work we did was, okay, can we pick up departures from routine? Somebody has a particular pattern, he deviates from the pattern. Is that possible can you pick that up? So that's an interesting academic problem. And it's this stuff that Google Now and those kind of apps use. So what's often done is you have some kind of entropy measure. And so this is just a function, and depending on where you are and the time, et cetera, it'll give you some kind of number, which is how much what your entropy is, how regular you are. But these things kind of break down when you want to look at higher level structure and you want to ask more complex queries. So another way of approaching it is model-based. So you define some kind of model how you expect people to move and how you expect departures from routine to happen. And this gives you more power, but it does build in more assumptions. So it allows you to look at different types of structural mobility. You can incorporate domain knowledge, for example, somebody's calendar information. You can deal with trust. You can allow for prediction, et cetera. And the work that James did was take a complete Bayesian approach. So, as a result, you have a probabilistic model, and which will give you a distribution over some kind of a path somebody took. Instead of just saying, look, this is the path the person took, no, you get a distribution which says, well, with high probability, this is the path you took, and there's different alternatives. So I don't know if I maybe should skip over this, but it's a probabilistic model which fundamentally it's always Bayes' rule, so I'm sure everybody's familiar with this. So the idea is you have some set of unknown parameters, in this case theta, and given your data, this is your posterior, you're trying to infer what the most likely values of those parameters are to match your data. And that's broken down into a likelihood and a prior, but I'm sure everybody's aware of that. So just graphically again, so you have a model with some unknown parameters, and the way it works in Bayesian inference is you first start off with assuming no prior information about these parameters, so could be anything. But as you get more data, your distribution narrows, and you get some kind of peak, and that will tell you what your most likely parameter values are. So same thing. So same thing here. You always start with a distribution, and as you get more data, and the distribution narrows, and then hopefully that gives you a nice narrow distribution, and then you have the right parameters to get your result. So one step further then is people then create Bayesian networks. How many people here are aware of Bayesian networks or know how they work? Okay, excellent. So everybody knows how it works, so that's really good. So it just allows you to factor out your joint probability distribution into different components, and you can specify the dependencies between those components or variables. And you can ask kinds of queries. So in this case, we have some kind of prior knowledge that it's cloudy or not. And then if it's cloudy, there's a certain probability the sprinkler will be on, there's a certain probability it'll rain, and given those two things, there's a certain probability we'll have, the grass will be wet. And then, of course, the interesting thing is, if we may not be able to observe these two things directly. We didn't see it. We didn't see it rain, or we didn't see the sprinklers turn on, but we do see the grass is wet. So then the question you can ask is, okay, what's the most likely cause? Or another question is, given it's cloudy, what's the probability the grass is wet? And so it's just a probabilistic model. Again, so then people already know this. So you can then, so that's just a static static problem, essentially. But you can add time as a dimension, and the canonical example here is speech recognition. So you have some kind of acoustic signal, which you sample at a certain rate, so time step 1, time step 2, time step 3. So you observe this acoustic signal, which has certain properties, and from that you try to infer what the phonemes are, which line up at each time step. That's okay, nothing particularly complicated. So, this is, again, just intro. So it's a probabilistic model, so you can run it forwards, i.e. you have a distribution, you can sample that distribution, and we can run it backwards, and you're doing inference, and you start with some initial prior. As you get data, your distribution will update. Anyway, so that's just background. So in particular, the model, what we built, so the idea is we want to model departures from routine. You want to pick up when somebody departs from routine. So what do you start off with? Well, the first assumption, you assume that everybody at every particular time step belongs, can be assigned some kind of location, some kind of fixed discrete location. And these locations correspond to, you hope, to points of interest. So at every time step, you assign somebody a label, okay, now he's in location 1, or location 2, or location 3, or whatever. So here, and so these are discrete latent variables. So we don't know what they are, but these are the things we're trying to infer. Then you're going to augment these latent discrete location variables. So this is a time step 1, time step 2, time step 3. And we're going to say, OK, so this location, well, there's 2 bits of information where it depends on. So we want to take into account the time of the day. Because knowing whether it's midnight or lunchtime or early in the morning, that should tell us something about where that person is. But we also want to take into account some kind of periodic time. So think, for example, the day of the week. So where somebody will be at midnight on Saturday evening is different than maybe midnight on Monday evening. So we want to take into account that kind of temporal information. So like time of the day and some kind of periodic time, say day of the week. Again, you do that for every time step. And then you add in a Markov assumption, which essentially says that where I am at this particular time step only depends on where I was once time step before. That's all we're assuming. So this is a simplification. It makes the inference and everything much easier and much quicker. But there's nothing inherent stopping you to make more complex assumptions that where you are now depends on where you were maybe 10 time steps away or what there's lots of complicated things you could do. But in this case, it's just a simple first order Markov property assumed. Then you add an extra piece of information. So, and this you add another latent variable, which is your departure from routine, which is binary for yes, I'm departing from routine, or no, I'm following a perfectly regular schedule. And so this departure value, again, it depends on the time of day and the day of the week. And it'll also give you information. It will also depend on where you are, what that location is. So you have this kind of basic structure for every time step, and for every person you have this model. Now, okay, so that just tells you a bit about sequential structure and about temporal information. But then you still need data. So if you're a user, you're walking around with your phone, there's GPS readings, the cell tower readings, you need to feed that data into this model, connect it up. So you have sensors. And there's different types of sensors. So there's just noisy sensors, for example, like cell towers. So they give you a latitude and longitude. OK, fine, you're here. But there's a variance associated with that. So it doesn't correspond to your exact location. It's the location of the tower. And then, so you need to infer the variance, and this depends a bit on where you are. So if you're in an urban environment, i.e. here, there's lots of cell towers around, there's lots of readings, and you can actually get a quite narrow distribution over your location because there's lots of towers around. If you're in a more rural environment, like to the left, so location 4 here, there's only one tower, there's only one reading, well, there's a very wide distribution of where you could be. So that's something you can infer. A different type of sensor is a GPS, which gives you a reported accuracy. And so you get different readings with different accuracies, but together, again, they help you narrow down where your exact location is. In the case, if you're looking at, for example, the riot data, for example, you may have eyewitness reports where you say, OK, somebody saw this person in this particular street or in this particular postcode or whatever. And then so there's a very wide variance there, which the person who made the eyewitness reports tells you that variance. But there's the issue of trust. Do you actually believe that? Is that right? Was that accurate? Is that reliable? And so in this case, the variance is given together with the latitude and longitude. But what you want to infer is the trustworthiness of that observation. And this is where the other observation types come in. So if if somebody says, oh, I saw this person there, but the GPS recordings or the cell tower readings contradict this, the nice thing about the Bayesian approach is you can all integrate that. And it's just that even though the person says, I'm very sure, but if it contradicts everything, the variance automatically increases. So that's part of the inference. So anyway, putting all the different pieces together, what you get is essentially this model, which is repeated for every time step, and every person has their own model. And so it's the same basic structure. So you have your latent locations. These are the things you're trying to figure out, where the person is at every time step. You have here this departure from routine score, so trying to figure out, is this normal? Well, no, is this in routine or not in routine? And then you have so your eyewitness reports, your cell tower information, your GPS data. These are just examples. each with their associated variances. And together that builds up the final model. And the details are not really important. It's all explained in depth in the paper if anybody's interested. So anyway, so this is fundamentally the problem you have to solve. So you have to find some kind of distribution over your model parameters, over all the locations you're visiting, over all the departure from routine scores, and over the trustworthiness. So these are your unknowns. These are the things you have to infer, given the observation data, and I think these are the variances of the observation data that are reported. So that's the information you have. You apply Bayes' rule, and you get some complicated formula. But essentially, this is what you have to solve. And so this is the inference problem that any Bayesian method requires. And there's many different ways of tackling this, but exact inference, unfortunately, is intractable. You can't solve that exactly just for complex models. It just doesn't work. So you need to do some approximation. So there's this. And again, this is not really my area, but so you can do EM, expectation maximization. It's something which is very fast, but it only gives you a point estimate. It doesn't give you a full distribution. It just tells you, this is the most likely location where you were, but it doesn't give you any kind of distribution over that location. You can do Monte Carlo methods where you sample, like Gibbs or Metropolis, and they do give you full distributions, but they're very slow. And you have somewhere in between a variational approximation, which does give you full distributions, and it's quite fast. So that's what was used here. But again, it gives you some advantages, and there's a reference there. But if people are interested, I would say just check the reference. So anyway, so we've built up the model. We can do inference, and that's nice. So inference will tell us about what are my most interesting locations, what are my main locations I visit, what's my departure from routine score at different time steps. It can learn about the noise characteristics of sensors. It can learn about trustworthiness, or which sensors are, in the case of iris reports, which are trustworthy or not. And the parameters you get full distributions, but you can interpret these intuitively way. You can express things in terms of belief or probability, and intuitively, that's people can understand that. And you can actually wind the model forward and start to do a bit of prediction. Where will somebody be? So many steps ahead, or when will somebody depart from routine given this information? So there's some advantages. So you can start looking at some performance data. So this was with an earlier version of the model. This is not work I was involved in, but Nokia released a data set of GPS tracks of various people. And you can try to see, you can compare different methods. And in this case, I believe it was indeed predicting departure from routine. And so there's different methods. The main one was, R1 came out on top, and that's the most important one. But anyway, this is more interesting, really. So this looks at, on the x-axis, you have an entropy measure. So this is, think of it as a departure from routine score. So the higher the entropy, the more you're departing from routine. So the more you're doing something out of the ordinary. And on the y-axis, you get how, the probability you're going to use a certain application on your phone. So this is part of the reason why Nokia was interested in this. And indeed, you see what you would intuitively expect. The more you're in an unfamiliar situation or an unfamiliar time, or you're doing something out of the ordinary, the more you're going to use email, the more you're going to surf the web, the more you're going to call people, the more you're going to use messaging apps. So there is a definite correlation there. So that's why it's interesting to look at, when do people suddenly depart from routine. So that was with Nokia data. So this is a different data set. So in this case, the Nokia data was all just GPS data, which was very nice and very easy to work with. So this is looking at heterogeneous observations, so cell tower, eyewitness, GPS, etc., and untrustworthy and trustworthy observations. And And we used, there's another data set called the Open Paths data set, which has mobility traces of people, and we use that as well to kind of build a synthetic data set we can test against. Because the big problem here is you want to get hold of realistic data because you want to benchmark how well you're doing. And that's actually very hard to get hold of. So you have to kind of craft your own that kind of hopefully makes sense. But you can do some performance on it and see how well it performs. So here it just says the number of days of observations, and here's the resolution in distance of how finely you can narrow down somebody's location. And you see that roughly after, I think it's roughly about 2 weeks or so, you can narrow down somebody's position up to about 60 meters in a kind of predictive way. And so, depending on the application, that's usually enough or not enough. But the main thing is just the trend. So as you get more days of observation, as you build up more observation, you learn about somebody's pattern. You can be more accurate in predicting, where they're going to go next, and the distribution over the possible locations really narrows down. So that's good. You want to see that kind of trend. Then looking at predicting actually departures from routine. So again, you see as we get more days of observation, as we get more readings, and your accuracy, so your precision actually goes up to around 70%, and then it plateaus off roughly. So after, 3 weeks of observations, you can predict somebody's departure from routine, relatively accuracy. And the recall is actually very good. Recall is very high, so you capture all the departures from routine. So that's very, very good, and these were really state-of-the-art results, and these are the ones we'll hopefully publish a KDD later this year. So then just to step back, so the implementation is just standard Python libraries, and there's a UI on top, which the purpose is just to understand if the predictions the model is making, does it make sense, are they intuitive, and there's nothing fancy there. Actually, just note all the inference and things was all written in custom code, though there are some libraries like GenSim, PyMC, BasePy, etc., which you can use, and that's maybe something to look up to do in the next iteration. There's also a lot of interest in probabilistic programming these days, and there's something interesting to check out in the future. But just to show you visually, so this just shows raw observations of a particular person, and in this case, they're all cell tower readings. So, these are all the readings that were taken. So the question is, so you have all these readings, but what's the path the person took? How did he move? Did he go from there down to there, or did he go, this way, or what's the path he took? And so this is where then you run the model on this kind of data, and then you get something like this. So this exact same view. And what you see is then this is the most probable path followed. So the model predicts, say, given all these observations, this is actually, I think, the path the person took. The main significant locations, so the L variables on the model, they are plotted here. So these are the locations the person spends, at least a reasonable amount of time. A lot of the observations disappear because when you go to the results of the model, the opacity of these observations is directly proportional to the departure from routine. So all the observations here, which were correlated with just very routine behavior, they disappear, and you're only left with the key observations. So these ones, they occurred at times when the person was actually departing from routine. So you get some kind of trace, and you get, and it's relatively accurate as to where, the path a person took. There's only 5 minutes, so just to illustrate just the inference. So this is a very regular pattern. So he's at work, and then he goes home, and then, he goes to the gym or something. Okay, that doesn't really fit, but because he doesn't sleep. But anyway, the only thing that matters is really you have 1, 2, 3 different locations where this person transitions through. So he's first here, then he goes there, then he goes there, and he goes back to the first location. It's a very, very regular pattern. So this is just an artificial data set. Then we can say, okay, now look here, we have the same trace, only this time. So he's up here in location 6. Now, usually, he would transition down to location 4, but in this case, he actually spends, a couple of hours longer in location 6 before he transitions to location 4. So this is an example of a temporal departure from routine. Usually he does this, but actually, for some reason, he's spending more time in a particular location than we used to seeing him do so. And so in the UI, you see that the model picks up on this, and so you get some circles, and you get a warning there saying, look, this something out of the ordinary there. And so this is a sanity check, because that's exactly what you want to happen. So that's an example. But anyway, maybe skip to the end. So this was a very a synthetic example, but if you look at real data, things are a lot more complex, and it's less intuitive to see why a person departs from routine. But anyway, you can compare different people. So in this case, there's 2 people, and they roughly depart from a routine at the same time. So you could say, are there correlations there? Or, there's different, does that tell you something about the social behavior, what kind of activities people do together, etc. There's lots of other things you can try to infer from that. Anyway, last slide, so summary. So this is just a kind of summary of the work we did, predicting people's departures from routine. So people, very regular pattern, but also departures from routine you can capture quite accurately. There's lots of limitations, though. Well, the main thing is getting good ground truth data, realistic data. So you'd need more data from people who know each other or using weather data. There's lots of app data which could be useful, and so that's something we're working on. And there's lots of more advanced things you can do. And the interesting one is, for example, a taxi driver. So a taxi driver, his routine is that he has no routine. He's going all over the place the whole day, all kinds of random locations. So, can you can just ignore that, say, okay, we won't deal with that. But still, is there something you can learn from that? So, that's an interesting question. Yeah, that's it. So any questions about this or references or whatever, feel free. Yeah?
Yeah. Is it possible to know whether this happened intentionally or unintentionally?
Yes. Okay. So that's one of the points, right? Somewhere I thought it was on there. Yeah. Okay. So there's also what. Okay, fine. You can detect when somebody's deviating from his pattern. He's going somewhere where he usually doesn't go to, or he's going in a different order, or he's staying somewhere longer or shorter than he's used to. So you can pick that up. Then the question is why? Why is he doing that? And we can't answer that. Here, then you'd need a lot more context information. But for example, the nice thing about this Bayesian model is you can import quite a lot of domain-specific expertise. You can put in information about a person's calendar, about maybe his hobbies or the other people he knows, and then you can build up a larger picture. If he plays football, for example, and he has a particular training schedule, but then maybe at some point it's a long distance. Well, he's doing an away match or something, or all that kind of context information you could incorporate. But that's a rabbit hole of its own. But that's a big problem. But you can try work at it. Yeah, go ahead.
Oh. Maybe you looked at predicting departure from routine or quantifying this probability of departure happening rather than detecting when it might relate to this intention versus.
Yes, actually, because if I remember correctly, these are detections. They're not quite predictions. So we have looked at predictions. And of course, the further you go ahead of time, the less reliable it becomes, and there's a tail off. And well, you have the full model, so you have the full distribution, so you can you'll see the variance spread out as you go further ahead. But I wouldn't be able to give you exact figures or accuracies on that. But yeah, so I can't really answer that. But hope with some more work we should be able to. Yeah. Yeah.
Yes. I'm wondering, is departure from routine best modeled as a binary variable or one that has a continuous interval, meaning you're somewhat following the routine?
Yes.
Or versus you're either following the routine exactly or you're never following the routine?
Yes, and that's something I didn't explicitly mention, but yes, indeed. So. And this is out of my comfort zone. You're asking the wrong person, really, for the exact details of how it works. But these are binary variables. Yes, a person is departing from routine or not. But on top of here, this is actually a continuous probability of a person departing from routine, which takes into account that binary variable. But so the exact reasons of how this works and how this is linked together, I can't really answer. But actually, if you look at the final model output, you do get a number between 0 and 1. So it's not a binary decision.
What I meant is not the probability of departure from routine. That I understand, but the degree of variance from routine, meaning that rather than going to one pub, they might go to one nearby versus going to one in another city across the world.
Yeah, no, indeed. So this is some. So I don't know enough about the underlying model, but I'm quite sure this is something that is, if not already captured, but I just can't explain it properly. But yeah, I agree that's something you should be intuitively able to do. So, but I can't answer it for sure. Yeah.
I was wondering, how much computational practice does it actually take to model a single individual? I ask because I'm sure he's being engaged in writing an Android app that will aggregate the info that a user is constantly squealing out to their self-provider, and it just shows it to them in a hit. And I'd really love it to be able to go, and this is the ability with which your software provider could predict where you were going to go next. Is that a non-starter? How much grunt for a single individual?
So let me think. So it's not, well, I don't think, so if we look at, so one example, there were roughly about 2 weeks worth of data, roughly in, I think, 10 or 15 minutes intervals at various sensors. And to train the model on that, so 2 weeks worth of data was roughly on a just, standard desktop PC, you're talking about on the order of half an hour to an hour or so. Yeah, just to train. And this is an offline model, so if something changes, you change the trust of some sensor modality, or if you make structural changes, you have to retrain everything. So I don't think it's something that you could just run on your app at this point, but a planned extension of this work is to look at online methods. So you can just bit by bit update the model as the data comes in, instead of having to retrain everything. So I don't know if that answers your question.